All right, 1.1 operations on real numbers. First thing is a definition. Definition is talking about a set. A set in math is a collection of objects, and they're notated with braces, these squigglies. You guys are more familiar with like parentheses or maybe even brackets. Well, braces are the same thing. So they literally look, you know, they look like this, and they literally in math they mean the same thing except for notation of a set. So like when you're doing the order of operations, you could do parentheses, brackets, or braces. But as far as notating a set, you have to use braces. And so here's some examples, like you might have the set A. And again, we just name a set by a certain letter. So set A is just the set of natural numbers, 1, 2, 3, 4, dot, dot, dot. And just a reminder, the dot, dot, dot just means it keeps going on and on and on. So 5, 6, 7, 8, and it keeps going on until basically infinity. And notice I have the braces around it. Without the braces, it's not a set. So those are the set of numbers that are in there. And the set B, notice I have the set B here. These are the even numbers here. So again, I have B equals and I have brace, 2, 4, 6, 8, and then dot, dot, dot. Set C, you can see the same thing. And then set D is just the number 1. The number 1 is in the set. All right, so those are examples of set and set notation. And here are the same examples, set A, B, C, D. So an element of a set is an object in the set. And you notate it, looks like sort of like a funny looking E to be able to do that. And so here's some examples of this. So here's my first example. 3 is an element of. So that literally means an element of set A. So if you look at set A up here, so look at set A. So 3 is an element. So there it is right there. So 3 is part of, it's in A. So 3 is inside of A. All right, so this one right here, the second example, 6 is an element of set B. And again, if you look at it, set B, the number 6 is right there. 1 is an element of C, which is true, it's right there. And 1 is an element of D, which is correct, it's right there. So those are some examples. I mean, you could get some, I could say something like 0 is not an element of A. So, because it's not, 0 is not inside of A. Or I might say 2.5 is not an element of set C, or something like that. So I mean, you can say, when you put a slash to it, it means it's not an element of that. So we talked about braces. That's how you use set notation, and we talked about the element of. Now a subset is just it's a set of numbers or objects inside of another set. So a subset is a smaller set within a set, and it's notated. Now this is this notation looks like a C, but it's like a stretched out C. All right, so here's some examples. So set B is a subset of set C. So here I have, and here I'm looking for like if this is a true or false statement, because it may not be. So for B to be this says B is a subset of C. Well, that means the elements of B. So think of all the elements of B, and then think of the elements of C. So is the set B, so are these numbers inside of the set C? Well, that's a false statement. So I wanted to throw in a false statement just so you understand that just because I write it here, it's not necessarily true. You have to actually look at the elements inside of there. So let's look at the next one, set D, and again, these are sets. The set D is a subset of A. So look at D. Is D inside of A? Yes, it is. The set D is inside of A. Now let's look at this next one. So that would be a true statement. The set C is a subset of A. Well, let's look at that. Is 1, 3, 5, 7, 9, 11, are those numbers inside of A? Well, yes, they are. So 1, 3, 5, all of the numbers of C, all of the numbers are C and C are inside of A. So this would be a true, a true statement. You've got to do that. And again, I could ask you tons of questions so far. Remember, we did elements of, so I could still ask you questions. You know, 1 is an element of A, or again, but if it's talking about a subset, we're talking about this whole set, like the set C is a subset of set A. So again, there's 2 different notations going on, the element of and a subset. Now here's an example of, it doesn't have to be numbers, okay? So remember, it's a collection of objects. So the set A is this is a set because I have braces. So it's all LCA students. So imagine every single LCA student, around 1,400 students are in set A. And set B is just a set of all the high school students. Set C are just the 8th grade students. Set D are just the algebra students. So I could ask you certain questions from here. So I could say, is Johnny, is he an element of A? Well, that would be true because Johnny is one of the LCA students. Is Johnny an element of set B? Is Johnny an element of set B? Well, we'd have to look at it. What grade is Johnny in? Is Johnny a high school student? If he is, then this would be a true statement. If Johnny is an elementary student, then this would be a false statement. So we need to know the information about Johnny, but that's how you would look at that, okay? And then, I could keep asking you about, Johnny is an element of C. Is he an 8th grade student? Is Johnny an element of D? Is he an algebra student? So again, that's using that notation. Again, you don't have to use numbers in set notation. Remember, they're objects. Okay, could be people, could be, whatever we're talking about. It's just they're objects inside of there. And again, I could use subsets. So I could say set D is a subset of A. So all of the algebra students are, I should say LCA algebra students, are a subset of all LCA students. So we're talking about LCA, the whole school. So the algebra students at LCA is part of LCA students. So this would be a true statement, okay? So we're not talking about all algebra students in the entire world. So anyway, so this would be a true statement. And then again, I can go ask you more questions about subsets or elements based off of these examples. All right, so if we talk about comparing and ordering is when I give you a set of numbers, a list of numbers, and I ask you to order them and place them in order, and then place them on the number line where they exist. So, and there's several ways to do this. You could put them all in decimal formation, fraction formation. It's totally up to you how you want to do that. Now, typically, I would recommend putting them all in decimal formation, but you don't have to. So this is already 5.6. This is 3.5 as a decimal. And then this right here, if you divide this, 25 goes into 6. If you divide that, that's going to be 4. And 1/6 as a fraction. And if you want to write that as a decimal, you would be able to get 4.16 with a bar. So if you put them in decimal formation, that's what they would be. And so then if we put them on a number line, we place them on a number line, we got 3.5 would be, or 3.5 would be about here. And then 5.6 would be approximately here. And then 25/6 would be here. And again, the reason why we just put them in decimal formation, so we can kind of see, does it belong here? Does it belong here? Does it belong here? We want to find out where on the number line should it be. And it's slightly past, if it's 4.4, we would put it a little bit further, like here or something. If it was 4.8, we would put it here. We'd put it more accurately. So 4.16 is just slightly past 4. and that's why I put it there on the number line. And the same thing here. Again, if I wanted to, again, there's several ways and tactics to do this. I'm suggesting that you put them in decimal formation. So 25 elevenths. If you did that, that would be about 2.27. The square root of 5 is 2.24. And I'm just rounding to the hundredths place. 3/4, you should know, is 0.75. And pi is a common 3.14. Most people know that. And so if we put this on the number line, we can see that the smallest, now these two are kind of close to each other, so we got to make sure we put them in order. So the square root of 5 would be about right here. And then slightly past that would be 25 elevenths. 3/4 would be about right here. And then 3.14 or pi would be right there. And again, I numbered them accurately, put them on the number line with the correct spacing. And lastly, let's talk about rational numbers. A rational number is a fraction of integers, a fraction of integers. So remember what an integer is. An integer is a number. Basically, when you draw a number line and you put the normal numbers on a number line, those are integers. So you have your whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then all the negatives of those. So a rational number is a fraction of integers. So notice this is a integer, this is an integer. So 5/3. Same thing with 2/7, 8/1. I mean, just about all of the fractions and numbers, like -7 can be written as -7/1. Whatever the number 8. I already have 8. So -8 is -8/1. 2/5. I mean, those are fractions, and that's just an integer over an integer. So here's some questions that you should be able to think about. Is the sum of two rational numbers rational? So if you take a rational number, add it to another rational number, will the result end up being rational? So think about that. I mean, if I had just a random rational number, so let's just take 5/3, and I add it to another rational number, say 4/5. So if I took those and added them together, would the result still be rational? Well, the answer is yes. They will always be rational. Now, how about the product of two rational numbers? So again, let's use the same two numbers. So 5/3 times 4/5. Oh, by the way, I forgot to write this. The result when you add those together, it's 37/15. So I forgot to write that. But anyway, so let's go back. Is the product of two rational numbers rational? Well, you could just multiply this and end up getting the answer and find out what it is. But the question is, will it always be? So is the product of two rational numbers? So my example, yes, when I multiply these two rational numbers, but would it always be that way? So any rational number times any rational number, will the result be rational? Well, the answer is yes. They always will be. So let's talk about, is the sum of a rational number and an irrational number. So an irrational number is not rational. So something that looks like pi or the square root of 3 or the square root of 7 or some square root that you don't know. That's what an irrational is. So if I take a rational number, so let's just use 5/3 again, and I add it to pi. Take a rational number and an irrational number. Would the result be rational? Well, it can't be, because pi is irrational, so the result will still be irrational. So this would be no. This is still going to be an irrational number. How about the product? Well, the same thing. If I took 5/3 times pi, pi is irrational. So when I multiply that together, it's still going to be an irrational number. So the answer would be no as well. The only exception to this is if the rational number I chose was at 0. So if I chose at 0 times pi, then the result would be 0, and then it would be rational.